So we're now going to start Module 7, and we had ended Module 6 talking a little bit about what happened with the Atchafalaya River and how when we do not discharge fresh water down the river, we see at the end of the pipe in Apalachicola Bay, Florida, how the salinities increase, and this can have an adverse effect on the oysters there in Apalachicola Bay, Florida. One of the things that can happen is that these oysters can be infected with a parasite, Perkinsus marinus, which thrives in higher salinities. And so as you can see here, it causes annual mortalities of 40 to 50% within the oyster population with these high salinities. Thus, as we decide to partition the water into Atlanta as opposed to Apalachicola Bay, we see tremendous effects on the harvestability of shellfish and the safety of shellfish within this region. In December of 2014, a real-time salinity, high salinity drought index workshop was held at the NOAA Center down in Charleston, South Carolina. And Dr. Paul Conrad of USGS rolled out his real-time salinity drought index, and this drought index is most critical. It tells us a lot about drinking water viability in drought. 15 to 20 years ago, very little of the drinking water in South Carolina and other coastal states like North Carolina was taken from surface water. Most of it was taken from groundwater. However, in the last 20 years, we have depleted a lot of the groundwater supplies with increasing urbanization of the coast, so that today almost 60% of the drinking water in the coastal zone comes from surface water supplies. So if we increase the salt content in these surface waters as a result of sea level rise and climate change, we render that drinking water unfit for human consumption. We also find that it's loaded with Vibrio bacteria as well as cyanobacteria that cause harmful algal blooms. So this poses a tremendous problem, and this workshop really, Dr. Paul Conrad of USGS rolled out his predictive, long-term predictive model for forecasting changes in these types of optimum conditions during drought. Sung-Soo Khan, in a dissertation conducted here at USC in the Arnold School of Public Health, found that Vibrio vulnificus levels were highly correlated with the disease state of Perkinsus marinus. And this is because Perkinsus marinus causes depletion of the anhydrin positive amino acids that are critical to successfully producing opsonin, which makes the mucus in the gills sticky. Under normal conditions, if you think of an oyster almost like you or I, if someone were to blow chalk dust in our face, we would, into our nose, we would immediately begin to secrete mucus and get rid of the chalk and dust out of our nose. Well, oysters do the same thing when they're exposed to microbes. They produce mucus and try to collect it and then slough that mucus off and get rid of the microbes that way. However, with heavy Perkinsus infections, they can no longer stick the microbial particles to the mucus because the mucus has lost its stickiness. And so under those conditions, we see very high levels of Vibrios occur, and they move from the mantle and gill labial pouch, basically the feeding apparatus where the mucus is produced, into the interior of the oyster to the hepatopancreas, the liver, which is essentially the liver of the oyster, and into the adductor muscle. This can prove to pose significant health risks to consumers. So one of the things we have to understand as we move forward with climate change, where we may decide not to put water into this watershed, into the Atchafalaya, maintaining the salinities, is when we may be making these oysters much more hazardous for human consumption. And of course, this becomes a very big deal. Well, earlier in this, the presentation, we talked about urbanization. And again, just to remind you, as we look at urbanization, it plays a key role in terms of affecting salinity and affecting, particularly during drought. When we have drought, the antecedent dry weather period between rain events is increased. So a lot of the contaminants, both microbes and chemical contaminants, are deposited out of the atmosphere onto the dry streets when it does rain and we have a major rain event. Therefore, if the loading is 10 to 20% longer than normal between rain events, as you often have in a drought, that means you may have a 10 to 20% increase in pollution load in the stormwater runoff. This just happens to be downtown Charleston at high tide when it rains. And this is very typical conditions because of the high rates of urbanization in Charleston, which ultimately end up running off into the Charleston Harbor and surrounding environments. Now, this is a study done by Marques et al. In 2010, looking at how climate change may affect safety of seafood. And so it talks a lot about understanding the interplay between ecosystem health and human health, and that continual interplay between oceans and human health. Traditionally, environmental studies have focused on man's impact on the environment and how man discharges from man and inputs from man alter the environment. But the ocean and human health aspect of this takes us a step farther and says, okay, if we do indeed adversely affect the environment, what does that do in terms of future human health concerns? And so climate change really adds another dimension to this by understanding the juxtaposition between changing ecosystem conditions and changing the potential risk to human health. This paper for both organic compounds, that is things such as pharmaceutical, personal care products, pesticides, PAHs, polycyclic aromatic hydrocarbons from road runoff of combustion from cars, as well as trace metals. You can see that in the dark gray bands and the gray bands, we basically see in the dark gray bands, the intersection of climate change enhances the toxicity in many cases, enhances the negativity of these chemical contaminants. And you can see as you move across the bottom of that slide, we see the greatest effect in phytoplankton, microbes, and some of the soft-bodied invertebrates compared to fish and other species, the annelid worms and things such as that. A good example of this is shown with grass shrimp. If we were to go out in a tidal creek here in South Carolina in the southeast U.S. and block seine and collect all the animals in the large macrofaunal animals in the tidal creek, 56% of all the animals are this one little species of shrimp called the grass shrimp. They're called the grass shrimp because they convert spartina, which is a major marsh vegetation, into detritus. And so what we find is that temperature tremendously increases the toxicity of many pesticides to shrimp. So thus climate change will enhance the toxicity as much as a factor of 4 or 5. We also see that salinity and temperature, the combination of those, may also tremendously increase the toxicity of certain pesticides to the grass shrimp. This happens to be chlorothalonil on the left, and so anyway, this and resmethrin, which is a mosquito control agent. So this really shows you that currently we have to understand how salinity and temperature interactions with these contaminant exposures, whether it enhances or reduces the risk of these chemicals. A lot of our evidence data suggests that it enhances the toxicity. Thus, current risk models used by the Office of Pesticides are woefully undershort in predicting adverse effects. In addition to pesticides and conventional, what we call legacy pollutants, we also have to be concerned about emerging contaminants, or what we call contaminants of emerging concern. These can include industrial chemicals, contemporary use pesticides, pharmaceutical and personal care products, and flame retardants. One of these classes of chemicals The pharmaceutical and personal care products are ones that we are focusing a lot of attention on, and I'll explain why in just a moment. I am a member of an expert panel to the state of to the state of California on developing monitoring strategies on these emerging contaminants. And we have put out a list of 12 dirty dozen chemicals, which include several contemporary use pesticides, several pharmaceuticals, including antibiotics. But this list of 12 compounds are the ones that we think pose the greatest risk to the environment. This is very important because in California, they are looking at water reuse so that they want to be sure when they take secondary treated sewage, they can reuse that water in a safe way without endangering the environment and human health. As I mentioned, the pharmaceutical and personal care products are a big part of the concern of this panel and other panels. There's actually a panel for the Water Research Foundation is also looking at this. Most pharmaceutical and personal care products enter the environment through patient use. The exception to that is the antibiotics, as over half the antibiotic use is from domestic animal use. And that makes the antibiotics different than the other pharmaceutical and personal care products. The U.S. Geological Survey did a study looking at some of these emerging contaminants of concern. And as you'll notice, the antibiotics were found at 48% of all sites across the nation. And clearly a class of chemicals that poses significant risk to the environment. If we examine the rates of antibiotic resistance around the nation, we see that antibiotics may be contributing to significant increases in antibiotic resistance. For example, in areas of Florida, if we look at the E. coli bacteria, these are human bacteria discharged from humans, as much as 13 to 25% of all the E. coli in surface waters are multiple antibiotic resistant bacteria strains of E. coli. We've all heard of methicillin resistant Staph aureus or MRSA. So these are all examples of illnesses that we're concerned about in terms of antibiotics. Now, I said earlier the antibiotics are a little different than some of the other pharmaceutical and personal care products because unlike the others, which primarily originate from human exposure through wastewater treatment plants, the antibiotics, however, half of the usage is in domestic livestock. The other thing that makes the antibiotics different is the ability of antibiotics to be persistent in the environment, and also the fact that antibiotics, unlike most chemicals, usually the higher the dose, the greater the effect. That's not necessarily true with antibiotics, and I'll explain that in the next slide in just a moment. This is a slide looking at a golf course here in South Carolina that actually land applies secondary treated sewage on the golf course, and you'll notice them moving from the retention pond for the sewage treatment plant all the way out to the green, all the way out to the adjoining waters. We see very high levels of antibiotic resistance, of oxytetracycline rather, the antibiotic that is often used to treat a number of illnesses in humans. So we clearly see the persistence of these chemicals that can cause antibiotic resistance in the environment. The other aspect of the antibiotics that make them different than the other chemical contaminants, usually the higher the dose of the chemical, the greater the effect. However, with antibiotics, it's just the opposite. If you do not have a full spectrum dose of the antibiotic administered, instead of killing the microbes, you actually induce antibiotic resistance. We say that typically you should have a blood level where you have the minimum inhibitory concentration, or the MIC. You'll notice at the bottom of the slide and to the far right, the concentration of antibiotic, you'll notice that it takes 24 hours or 72 generations for a naive strain, that is a non-antibiotic resistant strain of E. coli, to develop resistance. At 1/10 of the MIC, as we move back to the left, you'll see it still takes 24 hours before we see the first resistant strain. But you'll notice as we go to 100th, 1,000th, and 1/10,000th of the MIC, you'll notice that the time to develop resistance gets cut shorter and shorter. After 1,000th and 1/10,000th, you'll notice that we're down to a matter of 6 to 12 hours, which is somewhere around 18 to 36 generations of bacteria before we see resistance. So clearly the reason the doctor always tells you to take the full dose is so you do not create these lingering resistant strains, and that's what we see here. Evidence of these high rates of antibiotic resistance are found in stranded dolphins. Over 61% contain, we do rectal or blowhole swabs. We find that 61% of these animals have antibiotic resistant microbes, often resistant to as much as 10 different common antibiotics. In Charleston Harbor, where we have collected a live capture study, actually collecting dolphins, giving them a physical, where we do rectum and blowhole swabs, we find that they are resistant to 4 primary antibiotics: ampicillin, amoxicillin, ciprofloxacin, and penicillin. Now, again, if we take a look across the nation, these are different antibiotics that we find in areas for concern. We see things like triclosan, for example, the hand soap in most bathrooms today. It is an antiseptic. We also see the tetracyclines, ampicillin, penicillin. If we go to the Chesapeake Bay, we see erythromycin, sulfamethoxazole, trimethoprim. And if we look in the rest of the country, we see in Southern California, we see similar antibiotics being found, antibiotic-resistant microbes being found. Now, this next slide is a slide of the levels of different pharmaceutical and personal care products from the city of Charleston effluent being discharged into Charleston Harbor. And you'll note that the number one compound that we see here, I've got the cursor on, is caffeine and triclosan. So these are number one, number two, and then number three is ibuprofen. And you'll notice acetaminophen, some of the other painkillers, and are also found in fairly high levels. So clearly the triclosan hand soaps, and those were the one antibiotic, or in this case antiseptic, that the expert panel in California found to be a risk, a significant risk, and should be included in future monitoring studies because of the high prevalence rate in wastewater treatment plants. In this slide, this is a slide comparing rates of antibiotic resistance from different regions of the U.S. You'll notice that in Florida, we have in developed areas rates of resistance as high as 25% in developed areas, 13% in undeveloped areas, a difference of about 47%. If we go to Maryland, we see similarly 9% in developed areas, 2% in undeveloped areas, a 69% difference. In South Carolina, we see only a 3% rate of resistance in developed areas, a 1% rate of resistance in undeveloped areas, but an overall difference of 67%. Why are the absolute numbers of the amount of resistance so different in these areas? Well, in South Florida, the tidal range is 1 foot. In South Carolina, the tidal range is 7 feet. Thus, the amount of water that you can dilute the amount of antibiotic-resistant microbes in is much higher in South Carolina. If we go through and divide by a tide range of 7 in Florida, the numbers in parentheses that you see would be the South Carolina adjusted volume rates of resistance, which are almost identical to what we see in South Carolina. So the real solution, and similarly we see the same thing when we adjust for tidal range differences in Maryland with the numbers in parentheses. So clearly when it comes to antibiotic resistance, the solution to pollution is dilution, as the overall rates of resistance in developed and undeveloped areas are comparable. What makes the difference, the absolute amounts, is the tidal range. So one of the ways in which antibiotic resistance is developed is through these mutations. And what the microbes do is they produce these extracellular packets of DNA called plasmids that exist outside the microbe and contain the genetic code for developing resistance. So think of these as almost like a backpack that microbes can carry on the outside of the cell, and they can exchange among different species of bacteria. This means that there is a great potential for free-living marine bacteria like Vibrios to pick up these packets of resistant DNA from sewage effluent organisms from humans like E. coli. In the last module, in Module 8, we'll move on and begin to talk about how virulence related to climate change greatly enhances the antibiotic resistance among microbes, particularly the Vibrios. And is this related to chemical pollution, i.e. coming from antibiotics being discharged from sewage treatment plants, or is it caused by mutations occurring in the sewage treatment plant which put the packets of DNA out? And climate change, does it play a role in enhancing this effect? So we'll pick up on that in Module 8. So this last slide sort of reminds us of how important it is when we have urbanization within coastal areas with so many people. Where do we see high levels of antibiotic resistance? Wherever there's crowding. We see it in hospitals in the form of methicillin-resistant Staph aureus or MERS infections. MERS infections, there are more deaths in the U.S. from that than there are from AIDS today, over 19,000 deaths. We see it in hog farms and chicken farms, again, where we crowd organisms. And of course, the other place we see it is in the coastal zone, where we also crowd people and activity. So any activity which enhances runoff out of these urban areas into the adjoining marine and estuarine environment, we expect to see tremendous levels of antibiotic resistance in these coastal areas, which can be manifest in antibiotic resistant microbes that can cause wound infections, as well as antibiotic resistant microbes in seafood that may affect the seafood safety of the food supply. We'll pick up on this theme of antibiotic resistance in the last section, Module 8, as we begin to talk about examples of where we have seen increased rates of antibiotic resistance in parts of South Carolina, and what we might expect in the future with climate change. And what role does climate change play in all this?